Hello and welcome to Chapter 6 Notes. To place yourself, we had just finished talking about discrete and continuous variables, random variables specifically. And now I'm going to talk to you a little bit about probability distributions and repeated probability. So let's take a look at an example to start us off. So suppose you're playing a game and you're kind of stubborn, so each time you play, you're going to decide to play again, and especially when you lose, each time you lose, you're going to play again. So you're just going to keep playing till you're winning, till you win. It's kind of like the stubborn game. And each time you play, you only have a 10% chance of winning. So we're going to find some probabilities associated with this. The first thing we're going to look at is you play the game and you win on the first try. This is not a trick question. This is very simple. You have a 10% chance of winning on each try, each time you play, so it's just 10% or 0.1. Remember, we're going to use the decimals because when you multiply them, they actually make sense, unlike percentages. So be sure to use the decimals with all of your calculations. So what's the probability that you lose the first time you play? Or we're going to call this a failure when you try. So we're going to consider winning like a success and failure as a loss, unfortunately. And that's just 0.09. You're using the complement rule there. If you're 10% chance to win, then you must have a 90% chance of losing. Yay. Now read this sentence very carefully. The third time you play will be the first time you win. So you only have one win, and it happens on the third try. So your previous two tries, try number 1 and try number 2, you had to have lost. So the order on this is very specific. It goes, I lose, and then I win. And I thought I changed this so it didn't have the x's in there. That means times, but I don't want you to confuse this with x variable. And I didn't. I suck, evidently. All right. The 10th time you play will be the first time you win. So as you look back at C, there's another way I could have written C. I could have written 0.9 times 0.9 is 0.9 to the second power. Remember, exponents mean repeated multiplication. So here, since the 10th time I play is my first win, I must have 9 losses and then a win. So if you're picturing this, it's 0.9 to the 9th power, because there's my 9 losses in a row, followed by my 0.1 for winning. And there you go. This type of distribution has a very specific name. Let's learn what it is. It's called the geometric model. Yay! So this is a bunch of Bernoulli trials. Even though I haven't told you what a Bernoulli trial is yet, we will do that in a little bit. And it's what's required for your number of trials until you achieve your first success. So it's the stubborn distribution. And there are some things you might want to do that look like this. So you might ask yourself, why would I bother with something that I just repeat and then when I succeed, that's when I mark it? There are things like this that we want to model. These are usually what we call unlikely events. So you notice with my first example, I only did a 10% chance of win. So there are things out there like the chances of a tornado hitting your house. I know that doesn't seem like a win, but if you call that a win, you might wonder, oh, how likely is it that, in the 12th month of my home ownership, I'm going to get hit by a tornado, given that I know the chance of tornado in my county is like 0.3%. And that helps people like insurance adjusters decide how much they should charge you for insurance because they want to look at an unlikely event and when it happens. So even though it might not seem like a win, that's how we're going to look at this. We're a success. So our X is always the trial in which the first success is observed on. So thinking back with my last two examples, I did the third try as the first time you win first, and the third try, so we'd be counting as X equals 3 there, and the 10th try for D, would be the first try you win. That would be 10 as our X. So let's take a look at this. Our little p is going to be the probability of succeeding on one try. And then R is a positive number. This is just a placeholder for things like the stuff I just described where I was like, oh, the third time I win, my X is 3. And the 10th time I win, the X is 10. So just think of R as a placeholder as the counting of when this happens. And then the model looks like the following. So as you look at this, I'm moving my mouse now and hopefully you can see it, is think of it as the probability my success occurs on the rth try means I had to have one success and it was on the rth, whatever one it was. Rth try, and then I had to have R minus 1 failures before it. So think about the last example we did, D, where it was the 10th time we play was the first time we won. So our X equals 10 there. And so R is going to be taking on 10. So I have 1 minus P, or 0.9. R, which is 10 minus 1 or 9 losses, and then 1 win, which is 0.1. So it's just a placeholder in the way you calculate this. You don't have to use this formula if you don't like it. Here's another version of it that might be easier for you. We also use Q, which you look at it as like the flip-flop of P, as failure probability. It's the opposite of P, or 1 minus P. And then we can rewrite this formula with Q in it instead of 1 minus P, which is a little more natural looking. And we're going to keep using that notation, just so you know. So again, this is like things you repeat until you win, like tossing a coin until you get ahead, or shooting a free throw until you make one basket. Just one. You don't need more than one. Yay. So suppose a certain brand of chocolate, there's a 3% chance that you're going to get a golden ticket. Hint, hint, wink, wink. Please don't copyright bad things on this video. And you plan to keep eating chocolate until you find a golden ticket. Sounds like my kind of day. So let's suppose you eat a chocolate bar and the first one that you eat does not have a golden ticket. It's the probability of failure, so hopefully you recognize that's your Q value, 0.97. And then you're going to find your first golden ticket with the third chocolate bar that you eat. Okay, so that means I have to have 2 chocolate bars I eat that don't have a golden ticket and then 1 that does. So my success is occurring on the third try, or x equals 3. So my probability, remember x is the try on which the success happens. It happens on the third try. I have 2 failures, then a success, and if you multiply that out, you get the following probability, which is kind of small, but not too shocking, because if it's only a 3% chance, you should be thinking, oh, well, how many should I get? Or when should my success happen? Let's take a look at a slightly larger scenario. So suppose you want to see what's the probability you get it on the 100th chocolate bar that you eat. It's the first one that you got a ticket on. So here, x is equal to 100, so you're going to have 99 failures and then 1 win. And you notice that this is smaller than getting it on the third try. Now, this might be a shocker to you, but think about it this way. You did 100 tries, and your chance of getting a golden ticket is 3%. But this means I had 99 no tickets, and then on the 100th, I got it out of 100 tries. But 3% is 3 out of 100, which means you should have 3 successes out of 100. Yeah, so that means that in that 100 tries, I should have had 2 other successes that happened earlier, but they didn't happen. That's why this event is so unusual and so much smaller. So hopefully that makes sense to you. The other way you can think about it is if I have a 3% chance of winning, it should happen in 100 tries somewhere around the 33rd or 32nd try, instead of on the 100th try and not anyone sooner. So it's kind of like you missed 2 opportunities that should have happened, and bam, it happens on 100. And that just doesn't seem very likely. That's why this one's more unusual than B. Yay! So what's the probability that you'll find the golden ticket in 5 bars or less? So notice this is a slightly different scenario because it's 5 or possibly smaller, so that's less than or equal to. So when you think about the ways this could happen, is it could happen on the first try, could happen on the second, could happen on the third, could happen on the fourth, or it could happen on the 5th. And since these are all independent of each other, so you can't have it happen on the first and the second try since you're stopping once you get one, you can add all these. That's the only reason we're allowed to add these probabilities, is because they have no overlap. They're disjoint. And then it's just a matter of filling in the formula for this. So this looks a little bit of a mess. Prepare thyself. Yeah, it's not it's not impossible, it's just tedious. So if it happens on the first try, that's that 3%. Second try, that's I failed once, then I got it. Third try, that's 2 fails, then a succeed. 4 is 3 fails and then a succeed. And then 5 would be 4 fails and then a succeed. And this is actually pretty big, so 5 tries or less, pretty likely. Good times. Chocolate. You'll have to eat at least 6 chocolate bars before finding the golden ticket. So if you're thinking about at least, that means the smallest it could be is 6, but it might be larger. So this is greater than or equal to. And I'm hoping you've learned from our at least 1 or at least not none scenario that you always do these as a not or a 1 minus. So if you're at least 6, it could be 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I have to keep counting for infinity. I hope you realize this. So when you run into an at least with the geometric, you definitely want to do a subtraction. So if you ask yourself, at least 6 is 6 or larger. So what's not in here? Anything smaller than 6, or the stuff 5 or less. So I'm going to do 1 minus less than or equal to 5. So notice the difference since we eat whole chocolate bars, not partial ones. And that's just 1 minus the previous answer. Watch out for this with the at least, because very commonly they will have appeared somewhere else earlier. And so you get that 0.8588 for that. Let's look at something new. Oh crap, there's one more. I'm awesome. In case 5 seemed too simple, let's do 100. I'm not going to lie to you. If it's greater than or equal to 100, that's just 1 minus 99, or smaller than or equal to 99. And I use technology to do this because, I mean, 5 was fun, but this just seems like calculator nonsense, and there's many places where you can mess up. I'm definitely going to show you how to do this with Minitab when we get back from break. Good times. But, you know, I just wanted to make sure that you see that doing it by hand is kind of horrible, because you'd have to still do 99 of them in the scenario and add them all together. No, thank you. I'd rather do other things. All right, back to our 10% game. This is going to be a little bit different of a scenario. Like I said, this is going to be slightly strange, slightly different. So this looks like the same question, but it's not, because I'm going to ask you different options. All right. So we're going to find some probability. So notice the difference between this question and the last 10% game win is you still have a 10% chance of winning, but you're only going to play 5 times. You've got a set number you're going to do, and you're not going to do more than that. Cool. What's the probability? You're not going to win any of them. Sad times. Remember, it's only 10%, so this game must be pretty hard for you. This is like me playing, well, any sport where you have to throw things. So I'm hoping you predicted that, oh, if it's 10% and I'm playing 5 times, that's just, and I'm going to lose all 5, so I get to do 0.9 to the 5th, because it's 0.9 times itself 5 times. All right. You will win the first game, but lose the other 4. So your win happens on the first try this time. This is something the geometric couldn't do. So it's going to have 1 win and then 4 losses. Hopefully you anticipated that value. And now for something really weird. You win 1 of the 5 games. So when you picture this, you should be thinking, okay, 1 of the 5, but I don't care about order. So notice the difference between B and C is B tells me exactly where that win happened. It was on the first try, so it's in the first position. This one, it says you must win 1 out of the 5, so it seems similar, but where that win happens could be in the first position, the second position, the third position, the fourth position, or the 5th position. So if you're imagining what this looks like, it's kind of like, oh, I want my pen, thank you. I could have my win happen as my first try, and then I have my, oh God, this is wondrous, 4 losses, or it could be loss, win, loss, loss, loss. This looks beautiful. This makes you miss my handwriting on the board, doesn't it? Wee, and then it's in the middle, or it could be in the 4th position, or that's an L, or it could be in the last position. That was supposed to be an L. L, looks like I wrote a U. L, win. And hopefully one of the things you remember about multiplication is order actually doesn't matter when you're multiplying the parts to it. So this first scenario looks like 0.1 times 0.9, 0.9, 0.9, 0.9. It's that one. And the second one is I have a 0.9 here and then a 0.1, then a bunch of 0.9s. But you can rearrange that and combine your 0.9s. It's still going to be 0.01 times 0.09 to the 4th. The difference here is there's 5 ways that it can happen. Ha ha. I don't know how to make this advance. Let's hit this button. Yes, there we go. Oh no, that is incorrect. Crap. Let's cross that out because it's incorrect. So clearly copy and paste has done me dirty here. Because it should be 5 times this amount, right? So it should be 0. Oh, that's a beautiful 0.328. Can you tell I'm drawing this with my finger? It's not good. 0.5. Anyway, so clearly much bigger because there's 5 ways that it can happen, which is a little different from what we've seen previously. Here we go. So how about winning 3 out of 5? So if you're following the previous pattern, you're thinking, okay, so I have 3 wins. I'm going to have 0.01 to the 3rd and then 0.9 to the 2 squared. And then I got to figure out how many different ways this can happen. And this is a little bit of a harder scenario. So I'm going to erase this because I'm going to run out of space otherwise. Trying to keep track of all this. Ooh, that's fun. The red is interesting. I'm talking about this too much. So let's think 3 wins. So I could have all of my wins first. So win, 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 and then loss, loss. And then I could have loss, win, 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 loss, loss, loss. Who's getting tired of this? Win, win. I'm already at 3. Well, I didn't do this one yet. 3, L, W, L, W, W. That was fun. How about W, L, W, L, W? I like that one. I'm already at 5. Are there more? Absolutely. There are so many more. How many more are there? There's 10. And you should wonder how I'm getting that number. And I will definitely show you. And this is still not the... I tell you, copy and paste did me dirty on this one. Oh, boy. I really should blame myself, but I don't want to. I'm having a bad day. Anyway, so I'm assuming you guys know how to multiply. But if you do this, you will get... Wait, where did my pen go? There it is. This is awesome. So you get 0.081. Woo! Which makes way more sense because this is just a bunch of 10s times some 0.9s than that. And we're having a good day. So this is a new different type of scenario you're looking at in C and in D. It's where you can have a different number of wins, not just one, and it doesn't have to occur in the last position. And this appears to have a pattern of it. I have my number of wins times my number of losses, and then some sort of order that's happening. Let's take a look at this new scenario. So the first thing you need to notice is that we're actually doing what are called Bernoulli trials. What do Bernoulli trials look like? Well, there's only two possible outcomes, some kind of success and some kind of failure. So for us, that was winning the game or finding the golden ticket previously. And that's it. And that value doesn't, sorry, I'm thinking of something that comes next. Good job, teacher. And the probability of success, little p, is the same on every trial. You have the same chance of winning every time. It doesn't change. You have your same chance of getting the golden ticket every time. Doesn't change. Please keep note of that because when we start doing homework problems with this, you might be tempted to change little p. Don't do it. All the trials are independent, so we assume that winning or losing a game doesn't have effect on each other. So there's no psyching yourself out. There's no suddenly becoming better or worse at a game. There's always the same chance of winning. So we assume it's always on random chance. Now let's look at something we need to build the model we're going to get up to. Woohoo! Combinations! So if you're going to order K successes in N trials, it's the number of ways in which you can have this. So you might recognize, this is awesome, this down here. I'm down at the bottom. N factorial. And N factorial means N times N minus 1. Woohoo! Times N minus 2. This looks like nonsense. And so on and so forth until you hit 1, which seems crazy. Because looking at this formula, it seems like nonsense. So let's try it. Let's do one. We'll do 5 factorial. So what factorial does is it arranges objects in the number of them that you have. So if you have 5 distinct, as in they all look different, books that you wanted to arrange on a shelf, what you would do is you'd say, okay, I'm going to arrange them. How many ways could I arrange them? Well, when you go to put down the first one, you have 5 choices. Woohoo. And then when you go to put the second one, you have 4 choices because you've already used one book. And then you have 3, 2, and then 1. And that's where factorial comes from, when you just multiply all these together. P.S. That's 120, because you all know I can't subtract, but my multiplication can be strong. Anyway, so what factorial does is it tells you the number of ways you can arrange 5 different objects. We don't want to use factorial, though. We want to use combinations. So I'm going to do 5, choose 3, and that's the calculator command for that, in case you were wondering. Or I'm going to use it the other way, too. 5, choose 3. Woohoo! So just following the formula, that's going to be 5 factorial over 3 factorial, that's the K. And then this other factorial that's going to be here is going to be N minus K, so 5 minus 3. So this is going to be 2. Let's make it fit that weird shape I put in there on accident, 2 factorial. So as you're looking at this, this is I want to arrange 3 wins in 5 tries. This was the example I was doing in D. Sorry, I cleared my throat into the mic. That was bad. So basically what this is doing is all your wins and losses look the same. So when you're arranging your 5 objects, you're dividing out by the fact that all my 3 wins look the same and my 2 losses look the same. And that's what this is going to get up to. So this is going to be 5 times 4 times 3. Ooh, that dot's in a bad spot. Times 2 times 1. And then my denominator is going to look like 3 times 2. Wow. Times 1. If you can't laugh at yourself, what are you doing? And then 2 times 1. Wow, that last 2 is looking good. You'll notice 3 times 2 times 1 occurs in both the numerator and the denominator, so you can cancel those 2. And so in the numerator, I'll just have 5 times 4, which is 20. And the denominator will have 2 times 1, which is 2. And then 2 divided by 20 is 10. So that's where that 10 came from, where I told you, hey, there's 10 ways to do this, arranging 3 wins in 5 tries. It wasn't magic. I just did this. It's a fun time. So this is going to tell you how to arrange a certain number of wins in a certain number of tries, or a certain number of successes in a certain number of tries. Alrighty, so what we did was call a binomial. A binomial is going to have n total trials, and x is going to be the number of successes that you see in those n trials. And just like before, p is going to be our probability of success. Notice it's a little p. We use big P for just any probability or finding a probability. And then little q would be our probability of failure, or 1 minus p. So you'll notice that this has the combination to do the number of ways you can arrange your wins. Here's your probability that you have r wins, and then here's your n minus 1 losses. I apologize, I don't know if that rang through, but I just got a phone call, which I didn't know would email me through my computer, so that was wild. Anyway, so this NCR, that's counting R wins in n tries. Remember, X is counting your number of successes, and it's saying there's going to be R of them. So there's your P to the R for your probability of R successes, and then 1 minus P is your probability of failure, or also known as your Q. And then if you have R of them that are successes and you're going to try n times, then n minus R, you're going to have that many not successes or failures. The last thing I want to note is the mean and standard deviation of this distribution, because it's always the same. So if you're going to try to play a game n times and you have p chances of winning, it makes sense that on average you should win n times p times. If that messes with you a little, think about it this way. If you're going to try 100 times and you have a 30% chance of winning, how many wins should you have in 100 tries? You should have 30 of them, which is just 0.3 times 100, or n times p in that scenario. So it makes a little bit of sense. And then the standard deviation, remember, that's a measure of spread, or your average distance from the mean. So remember, when you're looking at this, it's like, oh, there's the mean. But remember, this is only counting wins. I also need to count my losses. So there's that. And then square root to keep the size down, as always. So hopefully that makes sense. Alrighty. Now, this is old data. This is from 2003. I'm sorry that that's what we have, but I'm assuming at some point one of you or two of you realize you have a grandparent that still doesn't own a smartphone. But suppose in the general population, 42% of individuals owns a smartphone. Don't get mad. We all know it's higher, okay? You randomly select a sample of 10 people. We're going to use the binomial to find some probabilities. First, we're going to find the probability that exactly 5 people will own a smartphone. So my number of successes is the 5 people that have a smartphone. My probability of success is 0.42. The number of times I'm going to try is 10. So you're about to see me write all that out. So number of tries, 10. What's my R I'm counting here? Well, it's 5. I'm not always going to write R. How many losses? N minus R, 5. So 5 have it, 5 don't. What's my probability of success? It's 0.42. Probability of failure, also known as Q, 0.58. And if you go ahead and calculate 10, choose 5, so 10 factorial divided by 5 factorial and 5 factorial, you get 252. I'm going to leave that calculation up to you. I'm assuming you guys can multiply and divide at this point, so that's another thing. If you do this calculation and you don't get the same thing I did, we should talk. Cool. So my probability that I succeed 5 times my 10 tries is the number of ways you can arrange it, which is that NCR, times 5 successes, so 0.42 to the 5th, times 5 failures, or 0.58 to the 5th, which you'll find is slightly bigger than 21%. Fun times. Alrighty, the probability that none of the 10 people in the sample own a smartphone. This one's kind of fun. So be thinking this is going to be none or 0. That's one thing that's different about the binomial from the geometric. In the binomial, you can get nothing. So this is P of x equals 0. If you do that calculation for the factorial, you do get 1. If you have a hard time with that, let me know. I will help you. 0.42 to the 0. Hopefully remember from exponentials that if you do anything to the 0 power, you get 1. So these are both 1s. That's boring because multiplying by 1 is nothing. And then you get 0.58 to the 10th. Wait a minute. Pay attention. Look at this. You totally could have done this without using the binomial formula. 0 of the 10 people will own a smartphone, which means you have just 10 people that don't own one, all in a row, and their order doesn't matter because they're all the same. So if you think about this, this is just 0.58 to the 10th. That's something you've been doing since, like, well, chapter 5. It's fairly small. Woohoo! Find the probability that at least one of them owns, out of the 10, will own a smartphone. Hopefully you've been paying attention. You know how we do at least. That's right. We're just going to do the opposite. So instead of at least 1 or greater than or equal to 1, we're just going to do 1 minus nothing, which is about 99.6%. I'm rounding more here. I got lazy when I was writing this one. Sorry. Let's do some more. the probability that less than 3 of the 10 people will own a smartphone. Now, this is my first time doing a less than, and watch how I write this because it's a little strange. So less than 3, we're going to think of as less than or equal to 2. The reason why you're going to want to make this change is when it comes to using your calculator to do a binomial or Minitab to do a binomial, it will only do less than or equal to. So it's very important that you know to rewrite these when you're using a binomial or a geometric even, because it only does less than or equal to. So stuff that'll be less than 3 will be 2, 1, and 0, or less than or equal to 2, which I've written out here. Probability x is 0 plus probability x is 1 plus probability x is 2. This should look fairly familiar to other scenarios you've seen using the geometric. Alrighty, so all I've done is written what the formulas are for these. So I've taken the liberty of doing the 0 one, which you should recognize from earlier, the 1 for 1, and then the 1 for 2. And then we're just going to calculate these and add them all together. And you get slightly bigger than 13%. Good times. All right, the probability at least 3 out of 10 people sampled will own a smartphone. At least 3. So that will be greater than or equal to 3, which is, as we've seen, whenever I encounter at least, I do it as a minus because there's just too many. Now in this scenario, you could totally do it like this one, where you just add up the number of ways it could happen. So at least 3 would be 3, 4, 5, 6, 7, 8, 9, and 10, because you only have 10 people. So this is a little bit different from the geometric because it doesn't go on forever. That being said, I already did less than or equal to 2 a second ago, so I might as well use it. 1 minus less than or equal to 2, or 1 minus the slightly bigger than 13%, gives you slightly bigger than 68%.